Welcome to the third little mini lecture on gates, truth tables, and equations. This is a digital logic lecture for assembly language. First thing we want to do is look at notation and precedence. And so notation, is a very important thing. How in the world do we write this? And unfortunately, as in many things, there are many different ways to write these different operations, but we have to understand them all. First of all, there's also an order of precedence that we need to think about. When you're multiplying things, you do that before you add things. And, the order at which you do things really matters. And if it's outside of the normal order of precedence, you need to put parentheses in your equations to emphasize that, so that somebody using your equation doesn't do it in the wrong order, which of course could cause the wrong answer. So in the order of precedence, the not, and or operators that we looked at last mini lecture here, not is the most important one, or the one we have to do first. So do not first, then do and next, and or last. There are several different notations for not. Sometimes people put a bar over it, kind of like you see down in this equation. Sometimes people use a circle for the for the not. Sometimes people use a tilde for the not, and sometimes people use this little cliffhanger gadget here as a not. These are all not symbols: bar, circle, tilde, and cliffhanger. For the and symbol, sometimes people use a star or a dot, like multiply. Sometimes people use an upside down V, and sometimes people also use an upside down U for intersection. For the or symbol, people usually use a plus, or sometimes a V symbol, or sometimes a U symbol. So several different examples. You see here an out equals the not of S and A. And you need to do this operation first. First of all, you do the not of S first, then you do the multiplication here. Hold that in your little memory for a minute. Go over here and take S and it with B. Get the result of that. And now or that with this. That's the operations you have to do. Here's another example. It's actually De Morgan's law. It says if we take A or B and we invert it, we get the same thing as if we took not A and we ANDed it with not B. Here's a couple other examples. Sometimes people write them like this. Actually write them out. And here you have it with the tildes and the crosses for times instead of even the star or the dot. They're using crosses or X's. So you'll see all this different kind of notation, and you kind of have to get used to it. Here's another example with a cliffhanger. This does the not, but you first have to do the or of X and Y. And here we have the not X, or intersection, which is and, not Y. This right here is the same as that, only they're using X and Y. Doesn't look the same, but it's the same equation. It's De Morgan's law. Okay, so let's look at De Morgan's law. It's actually quite a useful law, and basically what it says, if you distribute the bar, that means if you break this bar in half, you have to change that or to an and. Or if you distribute the bar here, in other words, break that bar so it's a and you have to change this and to an or. So if you distribute the bar, change the operation. Here's one way of looking at it. This is the top way. If we have A or B not, that's the NOR gate right here. A or B not, which is NOR. And that's the same as not A and not B, which is this gate right here. So those two gates are the same. Generally you see them written this way or diagrammed that way. Similarly, the second equation has this way of looking at it. Over here is the NAND gate. That's this guy right here is NAND, and this operation right here is A naught or B naught. And that's what this is. So how do we prove De Morgan's law? Well, actually it's very easy with a truth table. Let's just do it. And what this truth table does is shows you all the possibilities and just makes it totally clear. So here's all the possibilities of A along with all the possibilities of B. Notice you have every possible combination of A with B. You know, A could be a 0 and B a 0, or A a 0 and B a 1, or A a 1 and B a 0, or A a 1 and B a 1. So these are all the possible numbers here. If you notice, this is kind of like binary counting here. This is the ones digit, and this is the twos digit here. 2 to the 0 here and 2 to the 1 there. So if we do A or B, what do we get? Well, here it is, A or B. Now if we invert that, that's A or B not. Now let's try the other side of the equation and see if it's the same. So here's A naught and there's B naught. And now let's AND those two together. What do you know? It's exactly what we got when we did it with A or B naught. So we just proved De Morgan's theorem, at least for the top one. As an exercise, you might want to try the other one. So you should know how to translate logic from equations to truth tables to logic gates. And so all I can say is just let's do a little practice. They're basically different ways of writing the same thing. So here's an equation. It says out equals S naught and A and B naught, or S naught and A and B, or S and A naught and B, or S and A and B, and you can make that out of a schematic like this. So this first thing right here, S naught and A and B naught, that's this first term, and this guy right here makes the second term, and this guy right here makes the third term, and this guy makes the last term, and then they're all ORed together. So it's just basically taking that equation and translating it into a diagram. You can also translate that into a truth table. So you just put all the possibilities for A and B. It's kind of like counting here. Is the 2 to the 0, 2 to the 1, and the 2 to the 2, where you count. And so if you just do SAB, well, if you AND all those together, you get a 0. And you just you can look at what the output is here when you have all zeros on the input. So if S is a 0, then S naught is a 1, but A is a 0, so 1 times 0 is 1 and 0 is 0, so this is going to be 0 when you AND it with whatever. So here this would be a 1, and that guy's going to be a 0, so that's not going to make it. If this guy is it's always going to give you a 0, so if you are 0 or 0 or 0 or 0, you get 0, so that's how we got this 0. So let's look at the first one that actually gave us a 1. S was a 0, A was a 1, and B was a 0. So if S was a 0, S naught is a 1, right? Okay, so that's a 1. A was a 1, so a 1 and 1 is 1, and B naught was also a 1. So we've got 1, and we're ORing it with a bunch of other stuff, so we're going to get a 1. So that's how we got this 1, and you can look and do all the rest of them if you like. And it's this thing is identical to that thing, which is identical to that thing, and you should be able to go from this thing to that, or this thing to that, and actually you also should be able to go from this thing to that. So here's another example. We have here A naught going into this AND gate, B going into that AND gate, A going into this AND gate, and B naught going into this AND gate, and then we're ORing that together. So you can write it like this, or you can write it like that. And notice that this is basically just checking if A is different from B, which is the XOR operation. So what happens if we start with a truth table and try and do the other two? So here's what you can do. So you make, if you notice here, there's A, B, A, S, and B. So we're gonna there's there's 3 inputs. Okay, 3 inputs, and so you've got 3 of these guys right here. And so what you do is you go along and you look at right here. If every one of these that has a 1 on it, you need to include. So there's 1, 2, 3, 4. So we're going to have 4 of these things that are going to connect to the OR, because anything that has a 1, on the output would have needed to result from ORing with, something. One of these actually was a 1 when we got an output. So if you look at, you're going to have 4 outputs, 1, 2, 3, 4. That's why there's 4 inputs here. That's why there's 4 gates here. There are 3 things here. That's why you have 3 inputs on each one of these things. And now how do you figure out what to put over here? It's going to be an ASB, but it might have a not or a not. A not or not any not in front of it, just nothing in front of it. So if you look at here, this A naught SB, that would be for this one right here. That's the first one. So if you look at, in order to make these all 1s, you look at A as a 0, so it's A naught and S and B. So if we want A naught SB to give me that 1, so this is A naught SB is that line right there. And then this one right here is A S naught B naught, so that's this second one, A S naught B naught, that's that one right there. And this one, A naught S and B, A naught S and B. We don't need to do this because it's a 0, but we've got to get all of them, and that's an A, an S, and a B, so that's the last one, and we OR those all together, and we got that. And of course, you can also make the equations from this right here. You just kind of you take all the ones that have a 1, and you figure out what it came from. This one came from an A naught SB, so A naught SB, and so on. So you got all those kind of things in the equation right here, and hopefully it makes sense to you now. Okay, so there are some identities. These are Boolean logic identities, Boolean algebraic identities, and so these are something that are kind of like the properties. They're worth learning, looking at. If you take x and you OR it with 0, you always get whatever x was. If you take x and you AND it with 1, you always get whatever x was. That's called the identity property for OR and AND. And then if you want to get a 1, x OR 1 is always 1, and x and 0 is always 0. The idempotent property means that when you do that thing to itself, you just get the thing back again, and that's what you're both OR and AND are idempotent. The inverse, if you take x or not x, you get 1. If you take x and not x, you get 0. And the commutative property, that means if you're swapping x and y, x or y is the same thing as y or x, and x and y is the same thing as y and x, so and OR are both commutative. Associative means if you do, you have three things in a row. If you do these 2 first, you get the same as you do those two the second 2 first, and that holds for both OR and AND. Distributive property is kind of like if you do an OR on the AND of 2 things. That's the same thing as the AND of the first 2, or the AND of the AND x and y, or x and z. It's kind of like multiplication and addition have that kind of property. And then there's De Morgan's law, which we just looked at previously. So here's the next quiz. What is the logical equation in the truth table for the following circuit? Shouldn't be too tough, but I'll let you figure it out.